This is chapter 6 on work and energy. And I'll do a brief lecture today just on introductory topics of energy. This will be part of exam 3. And this will be comparing it, let's just say this is complement lab 6, which is on potential and kinetic energy. So we have our Newton's second law, F equals ma, where force is in newtons, this is in kilograms, and this is in meters per second squared. All right, that's Newton's second law. That was the basis of chapter 4. Now what we're going to have here is using the equations. Now if we go back to chapter 4, chapter 2 equations, one of our kinematic equations, v squared, is v naught squared plus 2a x, where a is acceleration, x is the distance traveled, v naught is initial velocity, and v final is v final squared is the final velocity. Now we notice here that when we have a constant acceleration, the longer we apply it for, the faster it's going to be going at the end. All right? So the idea of this and concept of this can be if we accelerate a car, all right? And it accelerates at some acceleration, 3 meters per second squared, right? Then if we do that for a short distance, it's not going to be going as fast as if we do it for a much longer distance. So the longer the distance we have the acceleration, the faster it's going to end up going. We're going to start relating this to the idea of work and energy. So another example of this is the barrel of a rifle, right? And we fire the gun, and the gas explodes and accelerates this bullet all the way just until it leaves. And at that point, the bullet is now on its own. But over this entire period is accelerating this distance x. So the longer the barrel, the faster it's going to come out at the end. If we only had a very short barrel, it'll explode quickly, accelerate just here, and then the bullet is on its own. So what we're going to find here is this relationship between force, because basically force is just the acceleration times the mass that's being accelerated, is related to this concept of work. All right? And this is in terms of energy. And the units for work, energy, are in units of joules or capital J. Right? So what we defined as work, use W, is force times distance, where this is in newtons, and this is in meters, and this will be, the force is applied in the direction it's moving. Right, so if they're both, so if you have a block, and we apply a force and move it over a certain distance d, if they're both in the same direction, then the work is force times distance. If instead we apply it at some angle, so we pull a block like this picture here, where you pull the block at an angle, so you're pulling it upward, which is actually probably easier to do. So the force is instead applied this way at some angle theta. The work is actually going to be then force times distance times the cosine of the angle between them. So it's the direction that it's going. I mean, if we pull the block straight up or pull it up, it's perpendicular and it just slides. We're not doing any work on it. So the work is a maximum if the force and distance are both in the same direction. And that'll be pretty much the basis of what we're going to be doing for this chapter, is simplified so force and distance are in the same direction. But keep in mind that, all right? So, all right, so what's another example of this? And then we'll get into the concepts of kinetic energy and potential energy. All right. If we have a block, all right, and we're pulling it so it accelerates, so the force is 10 newtons, and we pull at a distance of 20 meters, the work will be force times distance, which would be 10 times 20 would be 200 joules. In this case, if it's frictionless, then it's going to be accelerating all the way along, and then it'll be having, if we start from rest, then it will be actually having some speed at the end of this, given by the relationship V0 squared plus 2ax. Again, this is from chapter 2. So if it starts with V0 is 0, then that's 0. Then it's just V squared is 2a times the distance it is accelerated. Right? We talked about that in chapter 2, chapter 3, and such. Now if you lift the block, we'll get back to this one a little bit, but if we lift the block, say a block is 10 newtons, or it takes, so we have a block of 1 kilogram, mass is 1 kilogram, then its weight is approximately 10 newtons, because weight is m times g, and g is approximately 10 meters per second squared. So we lift that block, say 10 meters height, then it rises, that work done is force times distance, which would be 10 newtons times 10 meters, which would be 100 joules. This then would actually be so what we actually can do then is this is converting, doing work on this and converting that work into potential energy, which is given by mgh. So if we raise a block a certain height, we give it potential energy. And that can be done, can be dropped again. And we'll get into kinetic energy a little bit, but at the point here where it first starts, potential energy is 0. Up here, potential energy is 100 joules for this particular block. All right. So that's the case there of we'll deal with free fall. All right, back to here. We can't deal with this case. Remember our equations from, if we have V0 is 0, so we start from rest, then V squared is 2ax. Now, if we multiply both sides of these by m, the mass m, and then divide both sides by 2, we get the relationship 1/2 mv squared is ma times x, or this is equal to force times distance, x, force times x, let's just stick with x. So this then, this applied force over a certain distance gives us the expression for kinetic energy. So we call this kinetic energy and its units are in joules, and it's 1/2 the mass times the speed squared. So that comes directly out of the expressions we have from chapter 2. All right, so that's kinetic energy. All right, so what's the relationship to potential and kinetic energy? They're both energy. Well, let's look at an example here. I'll leave this up a minute as far as that's concerned. All right, oh, and I should emphasize this is always kinetic energy, 1/2 the mass times the speed squared. That's always the expression for kinetic energy. Potential energy, we're going to see, is different depending on what type of force we're applying on here. For here, this is gravitational. We'll look at next at a spring. All right, so let's go back to this problem here. And, all right, we have our expression for kinetic energy. I'll erase this just to make it simpler. Okay, kinetic energy is 1/2 mv squared. We take this block, start at rest, we raise it up to 10 meters, and then we drop it. When we drop it, what's going to happen? It's going to accelerate and get faster and faster and faster until just before it hits the ground. How can we then figure out what the speed is when it hits the ground? All right, we start from here, V0 is 0, because we raise it, let it rest, then we drop it. Now back in chapter 2, we could use our expressions for kinematics, of acceleration, distance, but we can also use this energy relationship to find what the speed is, what the kinetic energy is about. If we just drop this and there's no air resistance, then this is, and before it hits the ground, right? We have to before it hits the ground, so we call a conserved system. All right, we raise it up, drop it until it hits the ground, because once it hits the ground, you lose energy, it stops, energy, you make noise and all sorts of things. In that case, the total energy is constant, and this is given by the potential energy plus the kinetic energy. So the total energy is, in these kind of mechanical systems, defined as the potential energy plus the kinetic energy. So as this thing first falls, all potential, but then it goes faster and faster, becomes less potential, becomes more kinetic, until just before it hits the bottom, the kinetic energy, this all potential is converted to kinetic energy, and that's 100 joules. So up here, the kinetic energy is 0, because it was all stopped. Halfway down, so at 5 meters, it would be potential energy is 50, kinetic energy is 50, but the total energy stays constant, which would be 100 joules. We'll actually see as part of a graph, we graph potential, kinetic versus time. This is going to fall down. this is going to rise up so that the total energy stays constant. Okay. And this is done more elaborately in lab 6, I should say. All right. So based on that, the kinetic energy at the bottom is 100 joules. So how fast is it going just as it's bottom? What we can do, I'll leave this up a minute. Okay. So here's the important concept. Total energy is constant if it's conserved. Again, it has not hit the bottom. Once it hits the bottom, basically what happened is the total energy just go to zero because it stops. So this is the case until it hits the bottom. All right, so let's look at this then. Okay. All right, at the bottom, or just before it, I should say, kinetic energy, and I'll use KE, is 100 joules, which is 1/2 mv squared. All right, now what I have here is a mass of 1 kilogram, which weighs 10 newtons. But what we're going to do is then, this will be 100 equals 1/2 times 1 times v squared. Multiply both sides by 2. So 200 is v squared. V then would be approximately 14.4 meters per second. So that would be this velocity at the bottom. We could calculate it using our kinematic equations. And I'll do that just to compare. So let me get rid of this a minute. Now let me leave that up. All right, in our kinematic equations, all right, v squared is v naught squared plus 2ax. All right, v naught is 0, v squared is 2, I'm using g is 10 meters per second squared times the height that falls is 10. This would be v squared is 200. V would then be 14.4 meters per second. So this is back using the same thing. So you have the same relationship. This is back using the expressions for chapter 2. This is using kinetic energy and potentially converting. So we can actually find out what the energy is halfway down. Right? We could find, and then how fast is it going halfway down? We could do the same thing. Halfway down is half potential, half kinetic. In that case, halfway, and this is where this is going to be easier. This would be 50 joules. Right? Then that would become 100. 100. Then that would be 100. Yeah, 100. Because multiply both sides by 2, take square root of that, and we end up with V being 10 meters per second. Halfway down, it's going 10 meters per second. Okay. So that's how we're using energy. Again, total energy, as long as conserved, is potential plus kinetic energy. So that's the beginning part of chapter 6. So we talked a little bit about potential energy already, as far as that's concerned. Now keep in mind, this is one thing about energy, is kinetic energy is again, 1/2 mv squared. So if you double the mass, you just double the kinetic energy. If you double the velocity, you quadruple. It's double squared. So the kinetic energy increases quadratically with the speed. This is why things moving very fast can be very, very dangerous, because they have a high rate of speed, which then means they have a large kinetic energy, which means it takes a lot of force to slow them down. All right. Another example of this, if you go back to chapter 4 to some extent, but this concept here, right? Remember, potential energy is force times distance. So, as an example, again, you double the speed, you quadruple this. So, if we have an example, if you have a car going 10 meters per second, which is about 22 miles per hour, all right? It might take about 50 feet for it to stop with the brakes. So you're going a certain speed, you put the brakes on, it takes a certain distance, X, for it to stop. All right, depends on the brakes, depends on the mass car. Let's say it takes that same conditions. If you double that speed, because if you double the speed, 20 meters per second, which is about 44 miles per hour, you double the speed, you quadruple the kinetic energy. That means this is 4 times as much. The braking force doesn't change. This will become 200 feet. And if we go 3 times as fast, let's say 4 times as fast, 40 meters per second, which is about 88 miles per hour, which is pretty fast. We 4 times as much. This will be 16 times. This would be 800 feet to stop. Because the kinetic energy goes as the square of the speed, but so the square of this, v squared, will go, this will be 16 times that, so it'll take 16 times farther for it to stop. So that's the thing, that's braking distance and speed is significant in that regards. So keep in mind that this is potential energy, work applied, force times distance, kinetic energy. So, and I'm going to just look at one more here as an example. And this is an interesting thing. I'm not going to get into it other than qualitative wise, but this is the concept of pole vaulting. I used to coach pole vaulting, never really done it much myself, but I coached in high school. And the concept of pole vaulting is you run down the runway, plant the pole, and then want to go vertical. So the main thing is why the best pole vaulters have the greatest speed, because you convert that kinetic energy then into the pole, which then puts that into potential energy and raises you up as much as possible. Now you can add to that by using the fact that you can contort yourself, going over the bar, raise your body up as you take off, so you can actually add to that. But the main thing of pole vaulting is to get speed as much as possible, convert that into potential energy going up. Again, that's it there. Last thing I'm going to do today, and then I'll do some more examples later, is kinetic energy of a spring. All right, or potential energy. So potential energy, gravity, is given by mgh. If we have a spring, and this will be the only other one we're going to use, potential energy, if you take a spring, like a gun, like a pop gun type thing, and it's got a spring. It has a certain amount of force to compress it. If we compress it a distance x, all right, it takes a force to do that, and that force, this is x, this is force, is actually proportional to that. The farther you push it in, the harder it takes. This is actually what it is at the basis of a spring scale. So the harder you push it more and more and more. Unlike gravity, where you lift it, force doesn't make any difference how high you lift it. For a spring, the farther you push it in, the harder it gets. So in this case, the potential energy is going to be given by 1/2 kx squared, where k is what we call the spring constant. K, and this will be in units of newtons per meter. So it's actually the slope of this graph of force versus distance, where this is in newtons, this is in meters, and that's the spring constant, basically how much force does it take for a given amount of compression. It's given by 1/2 kx squared. So give a simple example. If we have a relatively strong spring where it takes 100 newtons per meter to compress it, and we press it, say, in this case, say 10 centimeters, which would be 0.1 meters, and potential energy be 1/2 times 100 times 0.1 squared, which actually turns out to be 0.5 joules, right? So if we push that there, let it go out, it'll compress to actually push that ball, give that ball kinetic energy of 1/2 mv squared, exactly from that. So in that case, that's what we have for a spring. So the potential energy for a spring is 1/2 kx squared. Potential energy for gravity is that, and kinetic energy is always 1/2 mv squared. Right? So that's the introduction part for chapter 6. I'll do more on this